In this video, I'll talk about constant volume reactions. The first law of thermodynamics tells us energy cannot be created or destroyed, but energy can be transferred. It's possible to change the internal energy of a system via two different processes, Q and W, heat and work. But when the system volume is a constant, we know delta V is zero. Therefore, the pressure volume work is equal to zero. And in this isochoric condition, we know the internal energy change is entirely due to the heat flow, again under isochoric conditions. If we are looking at a chemical reaction, the internal energy change of the reaction is equal to the amount of heat that flows in or out of this reaction system. If heat flows into the system, delta E is positive. If heat flows out of the reaction, delta E of the reaction is negative. And we have this simple equation that tells you the internal energy change of a reaction is equal to the heat flow under constant volume condition. Now I will show you an instrument called bomb calorimeter that's used to measure the heat flow of an isochoric reaction.
The major parts of a bomb calorimeter are an outer copper shell called calorimeter and the inner shell made of stainless steel where the fuel burns called bomb. Two fuse wires made of magnesium fixed to a 6-volt battery are used to ignite the fuel. A channel for the supply of oxygen is placed to help the burning of fuel. The steel shell or the bomb is enclosed inside the copper calorimeter. The calorimeter is closed from top using a copper lid. The space between the calorimeter and the bomb is filled with water. A mechanical stirrer is placed and on the opposite side of the stirrer, a thermometer is installed. The calorimeter is enclosed inside a capsule with an air jacket between the inner shell and the calorimeter and a water jacket between the inner and outer shells. During the process, fuel of a known quantity is placed inside the bomb and ignited. The bomb is filled with excess oxygen at 25 to 30 atmospheric pressure. The heat generated in the process is dissipated to water present in the calorimeter chamber. The mechanical stirrer is used to maintain a uniform temperature of the water. The amount of temperature rise in the water is noted using the Beckman thermometer.
This is a different diagram of the bomb calorimeter, but again you have a bomb here with a constant volume inside. The sample combusts inside the bomb and releases heat. The heat is absorbed by the bomb, by the water bath, the stirrer, and air above the liquid, this water bath level. This lead ensures that no heat is transferred or dissipated to the outside of the calorimeter. And then we have a nice equation here. Q of the calorimeter plus Q of the reaction is equal to zero. Again, this is because after the sample combusts, heat is released from the combustion. The amount of this reaction is Q subreaction. This is a negative number because heat is released. And then this calorimeter, including the water bath, the bomb, and this stirrer, even the air above this water bath absorbs the heat. Therefore, the Q of the entire calorimeter is positive because heat flows from the reaction to the calorimeter. We have this equation. Therefore, Q of the calorimeter is negative Q of the reaction. Now, let's work on one example problem. The heat capacity of a calorimeter is 2.0 kilojoule per Kelvin, and let's say we combust 10.0 millimole of a chemical, and that increases the temperature of the calorimeter from 20 degrees Celsius to 23 degrees Celsius, or from 293 Kelvin to 296 Kelvin. Let's compute the internal energy change in kilojoule per mole of the combustion of this chemical. So first, the amount of heat this calorimeter absorbs is equal to the heat capacity of the entire calorimeter times the temperature change. And the value of this is 2.0 kilojoule per Kelvin, and delta T is simply 23 minus 20, which is 3 degrees Celsius. What if we are using the SI unit Kelvin, the same value, 296 Kelvin minus 293 Kelvin equals 3 Kelvin. So delta T is 3 degrees Celsius or 3 Kelvin. And then we can compute this Q of the reaction. Q of the reaction is equal to negative Q of the calorimeter, and then we plug in the values, we get Q of the reaction is negative 6.0 kilojoule. And this is the amount of heat released from 10.0 millimole of this chemical. So if we want to obtain the internal energy change in kilojoule per mole, we need to use this value, the amount of heat, divided by the actual number of moles of the chemical. Therefore, the internal energy change of the reaction is, again, the reaction heat, which is negative 6.0 kilojoule, divided by the actual number of moles of the chemical being combusted, which is 0.0100 mole. The result is negative 600 kilojoule per mole. The meaning of this is if we combust 1 mole of such chemical, a total amount of 600 kilojoule of heat will be released from the reaction. Therefore, we have a negative sign here. The reaction loses energy. Now let's work on a practice problem. This time, the heat capacity of this calorimeter is unknown. We will determine its value. The combustion of 15 millimole of a chemical increases the temperature of the entire calorimeter from 20 degrees Celsius to 24 degrees Celsius. The internal energy change of the combustion of this chemical is negative 4,000 kilojoule per mole. Now let's determine this heat capacity of the calorimeter in kilojoule per Kelvin. So remember, we can use these two equations. The first equation is Q of the reaction is equal to negative Q of the calorimeter. And Q of the calorimeter is equal to its heat capacity times the temperature change. The second equation is this. The internal energy of the reaction in kilojoule per mole is equal to the amount of the heat of the reaction divided by the amount of the chemical in mole. So by using these two equations, you will be able to obtain the value of the heat capacity of the calorimeter. So basically, you need to use the number of moles, plug in here, the internal energy change of the reaction, plug it in here. You will obtain the value of Q reaction, and use this value at delta T. You will be able to obtain the heat capacity of the calorimeter. And remember this, a temperature change of 1 degree Celsius is equivalent to the temperature change of 1 Kelvin. The answer is in font size 2.